works. And finally, do I have another? Oh yeah, this one. I've got A transpose inverse. What is that? I'm going to show you that you can switch the inverse with a transpose. And again, why is this true? So all I wanted to show you is that the inverse of, so what this says is that the inverse of A transpose is A inverse transpose. So all I need to show is when I multiply this with this, I'm going to get back I. And that was going to show me that this is the inverse matrix of A transpose. Okay, so let's do that. Now, if I do, I'm going to start with the most complicated side and try to get to the other side, with the other side being I. So I need to write some equations in order to get I. So first thing I'm going to use is this identity AB transpose, that's B transpose, A transpose. But I'm going to read it backwards. So when I have two transpose multiplied together, which I have here, two things are transpose, I'm going to put them, I'm going to take the transpose of a product, this product being A. So you see this matrix here, A goes here, just like this A goes right there, and B goes here. So what goes here? It's this is not B, but this is A inverse right there. Okay, so the order of the multiplication has sort of changed. You see here it's A inverse A, here it's A inverse, but essentially when I multiply A with A inverse, I get I, and I transpose, well, what's I transpose? I is the matrix with all ones on the main diagonal and zeros elsewhere. You can check that if you transpose the identity matrix, you get back the identity matrix. Okay. In fact, if you transpose any diagonal matrix, so that's not just only true for I, but if you've got a matrix with a diagonal entries, if you transpose it, you're going to get back the exact same matrix. Okay, because the elements of the diagonals stay where they are. And since you've got zeros elsewhere, well, you're going to get zeros elsewhere after transposing again. So that's the proof for our for this thing. Okay, and so if we go back here, you see it means that you can permute the transpose with the inverse. So because of this, we're gonna write any of those as A to the minus t. So the notation here is clear because you can think of A to the minus t as either A transpose to the minus 1 or A minus 1 to transpose. It doesn't matter. It's the same matrix. So this you'll see in the exercises sometimes. If you have a matrix and it's written minus t, it's because you're transposing or taking the inverse, or taking the inverse and transposing. It doesn't matter. It gives you the same matrix. And that's it for properties of the transpose. Oh no, I've got two more things. That's a rather long video. One thing that's cool with the transpose is that, well, maybe I shouldn't use this because it's going to give you confused. Maybe this is our 1, 2, 3, this is our fifth property, okay? It's because this dot here means dot product. So if you've got U dot product V, okay, it's essentially, what is that? That's U1 V1 plus UN Vn. That's the same thing if you're taking the vector U1, U2, UN, and you're multiplying it by V1, V2, Vn. But usually we like to have our vectors being column vectors. So if you want to do this, if you want to write this row vector as a column vector, you can just transpose it. And now this makes perfect sense. So dot product, it can be written as U transpose V. So this is a pretty useful identity. And if you note, if you remember, those are equal. If you the dot product is, you can commute. So that's the same thing also as V transpose U. So so overall, you can you have U dot V, that's U transpose V, or V transpose U. It's the exact same thing. And I'm going to show you using this notation something that's pretty cool. If we go back to our projection of a vector x onto a vector a, you'll remember that we have the following formula. Okay, so this is a scalar here, and this is a vector, right? So we end up with a vector that's essentially parallel to a because we're projecting onto a. Now, using what I have above, you see I can write it as A transpose X over, and the norm, norm of A squared, right? You can write that as A dot product A. So you can write that as A transpose A times A. And here's the cool thing. I'm going to, what am I going to do? I'm going to put the A on this side. So it's okay because it's a scalar times a vector. I can change the order of the multiplication. It doesn't change anything. Okay. And finally, what I can do is put all of these as one big matrix multiplication. So I can write it as A times A transpose times X. And essentially here we're dividing by a scalar. So I can put my scalar anywhere I want to. I could say it's all divided by A transpose A. But since this is a scalar, I could say, well, it's just the first part that's divided by A transpose A. So you can check that. That makes sense. So what I have here is a matrix, and here I've got my vector. Overall, it still gives me a vector. Matrix times vector will give me a vector, so it's still the same expression, but the cool thing is that this matrix here, it's called the projection matrix. Is there a good notation for it? Maybe P. Okay. So P here, if I write it as A transpose over A transpose A, okay, once again, in the numerator you have a matrix, and in the denominator you've got a scalar, right? You can only divide by scalars. You cannot a scalar. You cannot divide by a matrix by a matrix. That doesn't make sense. But dividing a matrix by a scalar makes sense. So this expression makes perfect sense. And the interesting part is that if you do P times some vector X, that's actually projecting, that's going to accomplish the projection of X onto A. So that's why we call it a projection matrix. It's the matrix so that when you multiply by that matrix, you get the projection of the vector onto A. So maybe a quick example. Let's say you've got A, which is the vector 1, 2. Okay. The projection matrix would be A transpose. So A, oh sorry, I should write 1, 2 as a, it's always written as a column matrix, a column vector. So A is 1, 2. So if you look at what P is, it's 1, 2. A transpose is going to be 1, 2 like that. So 1, 2, 1, 2 divided by 1, 2 times 1, 2 like this. So what does that give you? Well, in the bottom part, all you get is 1 times 1 plus 2 times 2. You get 5. And over here, what do you get if you do the matrix multiplication? 1 times 1 is 1. 1 times 2 is 2. 2 times 1, 2. 2 times 2, 4. So you get the matrix 1/5, 2/5, 2/5, 4/5. It's symmetrical in the sense that the off-diagonal elements are equal. And if I do, let's say p times the vector, I don't know, minus 1, 1, okay? Well, what does that give me? It gives me minus 1/5 plus 2/5, so 1/5, and it gives me a minus 2/5 plus 4/5, 2/5. So I get 1/5 of 1, 2. So of course I'm getting a multiple of A because I'm projecting on A, but what that gives me really is the projection of the vector minus 1, 1 onto the vector A. So it converts the projection operator into matrix vector multiplication. So we can see projection as in some way as in terms of matrix multiplication, and that's pretty interesting. That was a really long video. I'm sorry about that, but there was a lot of stuff to say.